Since light is a wave, and since it's part of the electromagnetic spectrum, or EMS, that means that it travels at a certain speed. And all parts of the EMS have the same speed, and that is 3 times 10 to the 8th meters per second. Okay, this is a constant, and we refer to the speed of light as c. So anytime you see c in one of these equations, that's the speed of the light. Now, when you're talking specifically about visible light, then you are talking about frequencies that run from the high end which is your purples and your violets, and you're talking about low frequency, which are your reds. There is also invisible light. If we've got visible light, there's light that is too high of a frequency for us to see and too low of a frequency for us to see. Light that is below red, we refer to as infrared, or IR. Light that is higher than that, higher than purple, or higher than violet, actually, I should say, we refer to as ultraviolet, or UV. So that's all just to kind of put this in perspective. Okay, the fact that light is a wave means that it behaves like waves, and any other wave behavior that we've seen so far, specifically things like we have seen, just playing around with waves, that waves can be reflected, wave direction can change. In other words, it can be refracted. And it can also go through what is called diffraction, which basically means that as it passes through a narrow opening or around a corner, that it can spread out in all directions after it leaves that opening. And the fact that light does this, light can diffract around the edges of things, is one of the things that helped us to discover that light is a wave in the first place. Okay, let me swap over here and share my screen here. So I wanted to pull this up here. Maybe full screen. Okay. So we're going to talk a little bit about how light reflects. I'm just kind of taking it on faith at this point that y'all can still see and hear this. I am videoing it just in case things are cutting out. When light hits something and bounces off of it, that of course is called reflection. The most common way and place that we see this happen is with something called a plane mirror. Okay, a plane mirror just comes from plane, like you have in geometry. It just means flat. And when you have an observer that is observing something in a plane mirror, like say in this slide, you see here's your observer, there's their eyeball. The object that they're seeing in the mirror is this vase with the flower in it. What they're actually seeing is what is called a virtual image. Okay? And this virtual image that they're seeing appears to be the same distance away from the plane of the mirror as the distance that it is from the mirror on the observer's side. Okay? And so we assign these different things variables here. We say that the height of the object, that's HO, is equal to the height of the image, that's HI. And the distance of the object, DO, is equal to the distance of the image, that's DI. And when we're talking about distance, again, we're talking about the distance from the mirror surface. So that's the easiest one. For a plane mirror, DO equals DI and HO equals HI. It only really starts getting interesting when you start looking at mirrors that are not flat. And that's what I'm going to spend a little bit of time on. We're going to look at a few math problems on that, and then I'll take some questions from you. Now, when you're talking about a plane mirror again, since the height of the image is the same as the height of the object, it is not being magnified. And in our case here, magnified doesn't just mean making something bigger. It could also mean making something smaller. But it means that the image is a different size than the object that's causing it to appear. And so there's no magnification whenever you have a plane mirror. If you have a mirror that's not a perfect plane, however, then you are going to have magnification. The image is going to appear to be a different size than the object that's casting it. And you use this equation right here, where m is magnification. It's equal to the ratio of the height of the image divided by the height of the object. It's also equal to the negative of the distance of the image, or the distance the image appears to be from the surface, divided by the distance the object is from the surface. And this is an important bit right here. If your magnification factor is negative, then it means that your image is inverted. We say that your image is upside down. Easiest way that I can think of to demonstrate this, when you're done with this, go get yourself a spoon out of your silverware drawer and look at your reflection on that spoon. And you can look at it both on the inside surface of the spoon and on the outside surface of the spoon. In one of those, in both of those you're going to get reflection, but in one of those, the reflection you're going to get is going to give you an inverted image. Okay, and I will leave it to you to play around with the spoon later and figure out which one of those two is the case. The reason we call it a virtual image is because the image that we think we're seeing does not really exist. Okay? It's just all kind of a trick of our eyes. I think it's also important, if you take a look right here, and we're going to be coming back to this, whenever light strikes a plane mirror, a flat mirror, the angle from the middle, from the vertex right here, that it strikes at is going to be equal to the angle at which it's reflected. We call this angle right here the angle of incidence. That's what the I means. And we call this angle right here the angle of reflection. That's what the R means. So for a flat mirror, light, the angle of incidence is equal to the angle of reflection. Now, these are things that you all know because you've all looked in mirrors, or you've all played around with Instagram filters or whatever. But when you have a plane mirror, HO is equal to HI. The image is the same. DO is equal to DI. The distance that the image looks like it is from the mirror is the same as the distance of the object itself. The image is virtual because, again, what you're seeing there is not an actual projected image. The image is not inverted, so you don't see yourself upside down. However, your left and your right are reversed. When you hold up your left hand, the image of you holds up its right hand. Okay? Now, it starts getting really interesting when we talk about spherical mirrors. Okay? So, a spherical mirror, of course, comes from the fact that if you take a sphere, a hollow ball, and you slice a piece out of it, then what you're left with is kind of a curved slice. Okay? If you were to mirror either the inside surface or the outside surface of that, then it's going to make a spherical mirror. And there's two ways to talk about that. One is what is called a concave mirror, which is where you are looking at the inner surface. The other is a convex mirror, where you're looking at the outer surface. Now, in these diagrams right here, that point C would refer to the center of the sphere if the sphere was still all the way around that. Okay? C is referred to as the center of curvature. Whenever light waves come in and strike a concave mirror, the angle that they strike at is not equal to the angle at which they're reflected. And so what that causes is it causes images to have magnification. The same thing with a convex mirror. Light that is coming in from the outside and striking it is going to be reflected at a different angle from which it came in. So you're going to get distortion, you're going to get magnification. Here's where it starts getting really fun and interesting. We're going to talk about something called focal point. Okay? Your focal point, if you've got light rays that are coming in and striking the mirror in parallel rays like this, then when they bounce and they get reflected, they're all going to reflect and focus on a single central point. Okay? And that's referred to as F, or focal point. Focal coming from the same word that we get the word focus from. For a concave mirror, what's happening is that we're having light that's coming in and it's being reflected away. But for a convex mirror, the focal point is actually going to be on the other side. And so if you remember back from a couple slides ago when we talked about these plane mirrors here, the image that you see doesn't actually exist because it's on the other side of the mirror. And so it's virtual. The same thing happens with a convex mirror like this. The image you're seeing does not actually exist because all of these rays never intersect and meet. So the focal point is actually somewhere behind the surface of the mirror. You see mirrors like this. Trying to think. I know that like in convenience stores, they hang them up in the back of the store so that the employees can see if anybody in the back of the store is shoplifting. They've got one of these hanging in the school library. They put convex mirrors like this. Sometimes they stick them to side view mirrors on big pickup trucks because it lets you see a little bit further around you, gives you a little bit wider image than you'd be able to see with just a flat mirror. And of course, we're going to get into some interesting math with this. So the focal length, F, coming back up here, if you look in these two diagrams, the focal length is at a point that is halfway between the outer edge of that curved mirror and the center point, or the center of that sphere. And so we can say that the focal distance is half of the radius of that sphere. Same thing right here. The focal point, even though it's virtual, even though it's behind the mirror surface, is halfway between the mirror surface and the center of that sphere. And so it's half of the radius. And so your focal distance, or F, for a concave mirror, the one where you're looking at the inner curved surface, F is half of C. For your convex mirror, we say that your focal point is 1/2, or negative 1/2 of C. I know I've been talking an awful lot, and I apologize for that. So I think if I can keep this from killing the recording, I'm going to see if it will let me field any questions here. Looks like I've got a couple questions in the chat. Okay. How do you measure image height? And how do you pick up a baby elephant? Okay, I'll address the first one of those two. The way you measure image height is if it's an object, okay, so if it's an object, you measure the object itself, and then there are equations that let you calculate the image height. Okay. If it's a virtual image and it's behind the surface of the mirror, you can't actually get in there and measure it. The cool thing is, if you have a mirror that makes a real image, like one of these convex mirrors, then the image is actually projected somewhere between the object and the mirror itself. So you can literally have it projected onto something like a screen or a piece of paper, and you can use a ruler to measure how high it is. Anybody else have a quick question for the chat? Okay. I'm going to carry back on here. So whenever you are looking at either a concave or a convex mirror, you can use something called ray tracing to try and figure out where an image is located. If you've got, say for instance, we're going to look at this top one right here. Here's a concave mirror. We're going to have 3 rays coming in. One is going to be at the high end. It's going to bounce through the focal point. One is going to come from here. It's going to go through the focal point and bounce off parallel to the first incident ray up here. And then we're going to look at a ray that comes from the curvature point out to the edge. Now, what they're not showing you right here is that right here, well, no, that's not right. Forget I said that. Not all that. That part's correct, but forget the part that I didn't say that you wouldn't have heard anyway. So like, for instance, look at these examples. I like this a lot better. Okay, so here we have a concave mirror. We're going to have an object, and this object is going to be actually set further back than the center of the sphere of that mirror. It's going to be further back from C. So what we've got is we've got 3 rays. One ray is going to come from the top of the object. It's going to bounce off the mirror surface through the focal point and then come down here. Another one is going to come from the top of the object. It's going to go through the focal point, bounce off the mirror, and come right here. Now, if you look, the point where those 2 rays intersect is the point where the top of that image is going to be. And so in this case, if the object is set far enough back behind the center of the radius of that mirror, then the image is going to be projected inverted, but since it's actually on the same side as the object of the mirror surface, we say that this is a real image. So at this point, you could hold up a piece of paper at about that point and the image would be in focus. And so you could make a direct measurement. If you have an object that is between the center of the mirror, or the center of the mirror's curvature, and the focal point, we do the same kind of thing. We're going to take one ray that's going to come from the top of the object, it's going to hit the mirror, and from that point where it's parallel, it's going to bounce through the focal point. We're going to take one from the top of the object that's going to go through the focal point, hit the mirror surface, and then bounce off perpendicular to this top one here. The point where those two rays cross is going to be the top of the image. Now, I want to point out the difference between this one here and this one down here. This one up here, the image that's produced is smaller than the object itself, and so we have negative magnification. Okay, it makes a smaller image. This one here, if the object is close enough to it, the image is actually projected behind the object, but it's larger than the object was, and so you have increased magnification. Place where you see something like this at work is with one of those makeup mirrors. If you have one of those curved mirrors that you're looking into and you bring it slowly away from your face, then for a minute you're going to kind of blur out and disappear, but then as you continue moving back, you're going to see an upside down image of yourself. And as you continue moving further away, the image is going to continue actually getting smaller and smaller. For a convex mirror, it's a little trickier to think about, but you get the same kind of thing going on. What you're going to do is you're going to measure from the top of your object. You're going to have one ray, which is going to go off perpendicular to the top of the object. When it hits the mirror surface, the actual light ray is going to bounce away, but because we're going to be making a virtual image, you're going to continue ray tracing that ray down through the focal point, which in this case is behind the mirror. Then you're going to have another one coming off that is going to hit the mirror surface, and the point where it hits the mirror surface, again, this is aimed toward the focal point. The actual light ray is going to bounce away, but the opposite light ray is going to be continued on behind the mirror surface, and it's going to make a virtual image on the other side. Now this virtual image, if you notice, it's pointing the same direction that the object itself is pointing, and so the virtual image is going to be right side up. It's not going to be inverted. It's going to look smaller. How many of you guys know what it says on your right-hand side side view mirror on your car? Okay, I'll see if anybody wants to pop in. Anybody want to speak up on that one? Okay. It says on the right-hand side, objects in mirror are closer than they appear. And the reason why that's a thing is because the image that's made by that slightly convex mirror, which is designed to give you a wider angle so you can actually see more than what would be directly in front of it, the image that's made, that virtual image, is smaller than the object itself. And you can see in this one here, the object is moved further back, and in this case with the convex, the further away the object is, similar to what you have with the flat mirror, the further away the image looks, but look at how this one's traced with the rays. One ray comes off the top, bounces away, but the virtual ray continue on toward the focal point. This ray is aimed at the focal point. When it hits the mirror surface, it bounces away parallel to the ground. And the virtual ray continues on there, and the point where those two rays intersect is where your virtual image appears. So here's the mirror equation. And this is where we're going with this, and then I think we'll take a look, if I can keep from breaking things, and maybe actually look at a couple of problems that I gave you to mess around with. So mirror equation is 1 over the distance of your object plus 1 over the distance of your image. In other words, the inverse of dO and di